terminal velocity occurs when the resultant force, and therefore the acceleration, is 0, right? So in other words, it occurs when, no, hold on. Okay. It occurs when acceleration is approaching 0, right? Acceleration might equal to 0 at some point, and then you hit terminal velocity, but you might not actually get there, okay? What matters is that you're approaching it, okay? Obviously, this is the same because acceleration and force are just off by the factor of mass. This is the same as this. When acceleration is approaching 0, force is also approaching 0, okay? In this question, and this is not uncommon, they call this terminal velocity capital V, which is a little bit confusing because a capital V and a little v look almost exactly the same. So make your capital V's, comically large so you can tell the difference, okay? So let's have a look at this question. How would you even begin? Not a rhetorical question, actually. How should we begin? What would be the first thing that goes on the page when you have a look at this question? Any takers? I know it looks simple, but I think it would be helpful to have a picture, right? Just to get our heads around the situation. A particle is moving vertically downward in a medium, okay? Vertically downward. So right away, before I know anything else, I'm going to define the direction. I'm going to call it downward. That's the direction of motion. So I'm going to call that positive, okay? The medium exerts a resistance to the motion, which is proportional to the speed of the particle. Okay, that's fine. So here's our particle, right? And it's exerting a resistance upwards. Okay. It's proportional to the speed of the particle, not the square of the speed of the particle. And to save you a bit of time, I've already worked out it's going to be including mass this time. Okay, you can work that out if you spend some more time on it, but just so that we can go through this a bit quicker. Okay. The particle is released from rest at O. So we'll call this point up here, we'll call that O, the origin, okay? So its initial conditions times 0, okay? So you've got a displacement of 0 up there, and the initial velocity is also 0, because it's released from rest. So you've got V equals 0, like so. And at time t, its position, blah, 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 and its speed is v. Okay, and I've got a terminal velocity of capital V. And then they haven't mentioned it, but they've got it sort of in the equation. You've got gravity going downwards, right? And that's constant. Cool. So then you get asked to show this weird, awkward results. What we're required to prove is this. Gx plus v, 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 gt. Okay? So, this is a bit weird. This equation looks weird. It just seems to be random, okay? So, but rather than sort of thinking, well, I'll just randomly try things and see where we go. What is this? What is this? I would probably phrase it like this. Let me rearrange a little bit, okay? You can rearrange this in a variety of ways, but I think this is probably going to be most helpful. If I move this guy over here, like so, then I divide, that's common, so something like this. What have I got here? Oh, no, I shouldn't do that. I'll just take out that v. Divide by g, so that gives me t minus v on gravity. Okay, so I've just rearranged it a little bit. Now the reason why I did that is because now you can see what I'm working toward is a function of displacement in terms of, now this is a bit weird, time and velocity. That's where I'm headed. That's where I'm going. Okay? So that's going to define for me what kind of algebra and stuff I'm going to do down here. Okay? Now it's a bit unusual, and that's kind of why I'm picking out this example. It's kind of unusual that you have time and velocity there. That's going to be significant for us later on. Okay? But that's our destination. So let's see if we can make a start on this question. Algebraically, where have we started almost every question in mechanics so far? F equals ma. Good place to start. Okay, now off our diagram, we know what the force is equal to, right? I'm going to take both of these into account. One of them is positive and one of them is negative, okay? So I'm going to write up, I've got my mass times acceleration, okay? Gravity is positive in this case, minus mkv. So far so good? So from here I get an acceleration equation. An acceleration equation is a good thing to have. It's always a good thing to have because you can climb up from acceleration using your initial conditions up to something like displacement or velocity or whatever it is that you need. Okay. So I keep asking this. We have so many ways to write acceleration. Which way would you like to write it? Remember where I have to head. Now, in some ways you're like, I could kind of go two ways, couldn't I? You're like, I need to get to t. So maybe I would say dv on dt. You could say that. But then you're like, wait, I've got to get to v as well. So you might think, well, maybe I go dv on dx. Okay. Now, which should you choose? It's kind of funny because you've got two here. Eventually, we're actually going to do both. We're going to need both in order to get an equation which has both of these in it. Okay. Just for the sake of it, you have to pick somewhere to start. So I'm going to go v dv dx. Okay, I'm going to pause for a second. We've gotten to this point many times before. See if you can get to a displacement equation. X in terms of v. That's where I'm headed to. Can you get that out of that equation? I'll give you a few minutes to give that a go. Right, here's what I've got. This statement here, and I'm heading towards a displacement equation. I'm heading towards a displacement equation because that should be my final point. Okay, so I'm trying to piece the puzzle together. There's a pesky v hanging over there on the left-hand side. I don't want it to be there, so I can integrate properly. So I'm going to divide through. That gives you this. Okay, now, we've seen this problem before. We want to integrate, but it's not round the right way, is it, right? You can't integrate this with respect to x. You can only integrate it with respect to v. So I'm going to need this dv on the denominator. So I'll flip it, no big deal. Okay, dx on dv. That's a good thing to have that dx up there because when I integrate, it'll give me the x. Okay, and then you flip this over. But then you say, because you're like, that's not, which form is that? What's that supposed to integrate into? Okay, so I did give you a clue. There's a few different ways to write this, but I think the least intellectually strenuous way is to say, well, I need this numerator to cancel out somehow with the denominator because I can't integrate it in its present form, at least not easily. Okay, so therefore what I'm going to do is I'm going to rewrite this thing. I'm going to say, well, I need it like a g minus kv. So to start with, I'm going to need a factor of minus k up there, right? So if I make that numerator minus kv to compensate, because you can't just multiply things because it's convenient to you, except with regard to maths, I'm going to divide by minus k as well, right? So no net change so far. Is that okay? And that's getting closer to what I want. I need a g there, so if I have a g added, right, I should take a g away. So there you go, okay? Now, I have this bit on the numerator, so that can cancel out, and I'll just be left with this, and this will integrate into a log. That's really good, all right? So I've got minus 1 over k, 1, when I cancel, minus g over g minus kv. Okay, that's equal to dx on dv. Now I can integrate, okay? So I'll integrate this side and this side with respect to v, so you're just going to get x over this side, right? And then what does this mess become? Minus 1 over k. 1 just integrates into v. What does this become? Be careful. Be careful of chain rule in there, right? I think you're going to get, there's an extra factor of g, right? And then you're going to have to divide by, what are you going to have to divide by? K, negative k. Negative k. That's, in fact, that's going to become a plus over there. Is that alright? Watch out. I mean, you can test this out. If you take this guy, g minus kv, plus a constant, okay, what happens when you differentiate him? Well, he'll become minus k, chain rule, right, over g minus kv. The minus will come out the front, and that k will cancel with that k. So you're good. It works out. Right, you take your initial conditions, which I just rubbed off. You find out what your constant is, and it turns out to be, I think, minus 1 over. I'm gonna expand this. I think it works out to be, what is it? G over k squared? Or is it G over k? G over k squared log G. I think that's right, okay? So you've got a plus log here, you've got a minus log there, you can put them together, they've even got the same coefficient, which is nice, okay? So I'm gonna slap them both out the front, like so. Minus V over K, which looks like a royal mess, doesn't it? Okay.